Hello everyone, my name is Zeliang Zhang. The theme of my report is Trillion-Tensor, Trillion-Scale CP Tensor Decomposition. Here are the motivations of our work. First, tensor decomposition is the basis of many machine learning applications, including graphical analysis, image classification, and data mining. There are two major tensor decomposition models, CP tensor decomposition and Tucker tensor decomposition. Second, in recent years, the size of tensors becomes increasingly large, approaching millions to trillions of non-zero elements. Due to the limitation of the main memory, both CP and Tucker algorithms are impractical for large-scale tensors. Third, many proposed methods may handle tensors with each mode up to millions. However, the input tensors are required to be extremely sparse, where the total number of non-zero elements is up to millions. So, there is a large need for exploiting the high-performance large-scale tensor decomposition scheme. The challenges in our work is summarized as follows. Designing a compression method to process an out-of-memory tensor, exploring an appropriate trick to recover the permutations and scaling of the four-mode factorization matrices, implementing efficient parallel schemes both on CPUs and GPUs respectively. Here is the overview of our proposed Trillion-Tensor decomposition. The Trillion-Tensor decomposition algorithm mainly consists of three stages, namely compression stage, factorization stage, and a scaling and permutation stage. First, a tensor will be split into many blocks. Here are 27 blocks. The tensor will be compressed into 8 replicas. Second, each replica is factored to mode matrices independently, using CP decomposition. Third, with a proper permutation and normalization, solving a least squares problem for each mode will result in the four-mode matrices. Back to the large-scale tensor. Using the factorization of the first block, we got the permutation matrix and the scaling matrix. Then we use them to obtain the four-mode matrices. However, the computation complexity of the compression stages is really high. Huge time consumption of the compression stage is the bottleneck of our algorithm, with the size of tensors increasing rapidly. So, we propose two methods to accelerate the algorithm. First is the parallel implementation on CPUs. This scheme advocates exploiting the property of multi-core process on CPUs. Second is the parallel implementation on GPUs. This scheme advocates exploiting the GPU's high performance on matrix multiplication. Here are the performance evaluations. For each case, on scales ranging from 100 millions to 1 trillion, we first generate the model matrices from an independent normal distribution, and we set the size of each mode ranging from 1,000 to 10,000. This figure shows the comparison of the mean squared error between the baseline and the optimized version. And this figure shows the comparison of the time consumption. As you can see, for trillion-scale tensor of size 10,000 times 10,000 times 10,000, we reduce the baseline time of nearly half a day to no more than 6 hours, and we successfully control the mean squared error under a relatively low magnitude. Thank you.